Hello everyone, welcome to my video on Riemann sums. So we ended the last video with this same definition on how to find the area of a shape where one of the sides is curved. But now we're going to look at three specific cases. We're going to look at the left endpoint, we're going to look at the right endpoint, and we're introducing now the midpoint. So let's go ahead and do that. So the definition is the area A that lies under the graph of a continuous function f is the limit of the sum of the approximating rectangles. This is what we saw. We took the area under the curve by creating little rectangles underneath, approximating the area and adding them up, and that gave us the entire area. Now we're focusing here on the left endpoints. So when we say the left endpoints, we're saying that the left corners of the rectangles touch the function. So as you can see here, the function's in green. The red rectangles, it's all the left corners that hit the function. This hits the function, this one, this one, this one, and this one here. Okay, so the definition, the area is equal to L of n, so L for left endpoints, n is the number of rectangles. So depending on how many rectangles we're going to cut it up into, that's our n. And it's equal to the limit as n goes to infinity, open bracket, delta x times f of x0 plus delta x times f of x1 plus dot 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 all the way to delta x times f of x subscript n minus 1. So notice here, this is different from the last definition that I gave you in the sense that here we had x1, not x0. This is the only slightly different thing you have to catch. It's the fact that the index or the subscript of the x starts at 0. Because the left endpoint hits the function, this would be at the case where x is equal to 0. If you were doing the right endpoint, you would be starting at the case x equals 1. We're going to see that later on. So for left endpoint, keep that in mind that you start with the index I equals 0. That's the slight difference. So you start at x equals 0, that's the first one. The second point where we hit, we're looking for the height of the function is at x1, then x2, x3, so on and so forth. So if you have your function over here, all the left points are hitting the function. The delta x is the width or the thickness of each rectangle, which we're going to assume to be the same for the case of simplicity. And f of x1 is the height, or f of x0 is the height of the function. Okay, so over here, for example, I have x3 is over here. The height of the rectangle corresponds to f of x3. Okay. So now what I'm adding to this is the fact that we have delta x is equal to b minus a over n. This is an added formula. You can figure out these values here, your x values, using these formulas here. So keep these in mind, so these have to be memorized. You could do this intuitively, but it's always good to have a formula in case the numbers are hard to work with. So the first one is delta x. How do you find the thickness? Well, to find the thickness depends on how many rectangles you're going to partition it into. So in this case here, I drew 5 rectangles. So we're going to take b minus a over n. So b and a is the starting point, it's the first x value, and b is the last x value. And when we partition it, we're going to cut it up into, let's say, in this case, I drew 5 rectangles, so I'm partitioning this interval into 5. How would you do that? Well, you take the largest value and the smallest value and subtract them. That gives you the distance of this interval. So we do b minus a, and then since we have 5 rectangles, we're going to divide it in 5, and that gives us the width of each rectangle. That's delta x. Okay, so this is what the formula is telling us over here. And then secondly, we have xi. How do you find the actual value of each x? Well, you use this formula. Once you find delta x, you can use it and plug it into this formula to find the value of each x. The index that we're using is I. And let's say I want to find x1, well, I'm just going to substitute this with 1. How do I find that? It's going to be equal to a, which is the starting point, your first value, and then you're going to add 1 times a delta x, right? So you're going to shift over by 1. If I wanted to find, let's say, x3, well, it's the same thing. You're going to start at a, and this is saying plus 3 times delta x. You're going to shift over from a by 3 delta x's, the width 3 times. That's going to give you the x3, okay? So this is the idea. These are 2 formulas. Keep them in mind. And we'll use that to find the actual values depending on how many rectangles we have. So if they tell us to partition the 4 rectangles, we'd use 4, we use this formula. If they don't give us the number of rectangles, n, then we assume it to be n, and we just still use these formulas here, just not plugging n as a value. Okay, so now let's take a look at the right endpoint. So here now we have the right endpoint. So same definition. The right endpoint, essentially the right endpoints of the rectangles hits, or the right corners of the rectangles hits the function. So here now notice that the right sides of each rectangle, the right corners hit the function. So that makes it a right endpoint problem. So we use the notation arc sub n depending on the number of rectangles. And here we have the limit as n tends to infinity of delta x times f of x1 plus delta x times f of x2 plus dot 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 plus delta x times f of x subscript n. So here, notice the difference is instead of starting at 0, now we're starting with subscript 1. The index is 1. Why? Because the first corner point that hits the function is at x1, not at x0, like the left endpoint. Okay, so that's why here we're starting at 1, and we're finishing at the last one, xn. Notice at xn, the red endpoint of the rectangle hits the function, whereas for the left endpoint, we had to stop at x subscript n minus 1, 1 before the last endpoint, because the last left endpoint to hit the function was at xn minus 1, whereas here the last endpoint is at xn. Okay, so keep that in mind. For a red endpoint, you're starting with index 1 and you finish at n, whereas left endpoint, you start at 0 and you finish 1 less at n minus 1. Okay, but other than that, it's essentially the exact same thing. We're using the same formula, delta x equals b minus a over n, and we're using the same formula, x subscript I equals I plus I times delta x. Everything is essentially the same. The only main difference is the fact that the subscript that you're starting with is at 1, okay? So I equals 1, okay? And that's how we find the red endpoint. Let's go ahead and look at midpoint. So our final case over here is the midpoint. So the function passes through the midpoint of the rectangles. So we use the notation capital M sub n, and that's equal to delta x times f of x subscript 1 bar plus delta x times f of x subscript 2 bar plus dot 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 plus delta x times f subscript f of x subscript n, all that bar. So what does the bar mean? So first of all, delta x, same thing, it's b minus a over n. 2, to find xi, again, same thing, a plus I times delta x. But the bar is essentially, once you find your xi's, you're finding the average of each xi of each term, okay? And this makes sense because we're using the midpoint, right? So the rectangles, the midpoint of the rectangles hits the function. This is what we care about, okay? And how do we find the value? So once you find your x0, x1, what's the midpoint of x0, x1? Well, it's just the average of those two values. So that means this value here, to find the x value corresponding to this point here, the red point up here, is this one here, is, I'm just gonna write it on top, is x1 bar, okay? And then how do you find the height? Well, it's f of x1 bar. And same here, between x1 and x2, I don't want to write too much because I don't have that much room, but this is x2 bar, okay? This point here would be x3 bar. Same for here, x4 bar, so on and so forth, all the way to xn bar, okay? And then you can find the height at those values, at those respective x values, and that gives us the midpoint. The midpoint, in my opinion, is the most precise out of the three, out of the left and right, because as you can see, taking the midpoint, it lowers the amount of error. So midpoint is probably the most accurate one to use. But there is a bit more work because you have to go ahead and find the midpoint, so really depends on the problem. So again, here we have to start with the index I, and when you take the midpoint, it's always 1 larger than the value that you start with. So we started at x0, you're taking the midpoint of x0 and x1, so that's x1 bar, okay? And this is the formula, and that's it. So let's go ahead and take a look at a couple of practice problems. So in this next example over here, it says to estimate the area under the curve of the function f of x equals x squared minus x on the interval 0 to 2, using 4 rectangles of equal length. We're going to use left endpoints. Let's go ahead and do that. If you want, you could try to sketch this first. I think it's always a good idea to sketch. You don't have to, but I think sketching is a good idea. So let's begin by doing that. This is a quadratic function. We have x squared, and the coefficient of the x squared is a 1, so it's positive. It's opening upwards. That helps us out. And if we go ahead and find our zeros, we could factor out an x, giving us f of x equals x times x minus 1. Setting that equal to 0 tells us that x equals 0, or x minus 1 equals 0, which tells us x equals 1. So we know this is going to pass through the origin, 0, and it's going to pass through 1. We just care about the interval from 0 to 2. So this is going to look something like, we know it's opening upwards, and it's passing through these 2 points, 0 and 1. So the only way for that to be possible is if it looks something like this. Okay, just to have an idea. Okay, so we'll keep that in mind. We have to go use our left endpoint, and we're partitioning it into 4 rectangles. So this is important, 4 rectangles. that's telling us that n equals 4. So the number of rectangles we're going to use is 4. So using our formula, we're using L4, and because we're not making the rectangles as small as possible, we do not have to include the limit now. We're splitting this up into 4 rectangles and finding the area of each, adding them up, and that's our approximation. So what we have here is essentially, without the limit, it's delta x times f of x. Since it's left endpoint, we're starting at 0, plus delta x times f of x1. I'm running out of room. Let's do it down here. Delta x times f of x2 plus delta x times f of x3. Right? We have 4 rectangles. We stop 1 short. Remember, using the formula was n minus 1. We stop at 3. This makes sense. And all these terms have a delta x. So if you want, you could just factor out a delta x, giving us delta x, open bracket, f of x0. You don't have to do it this way, but you could if you want. F of x1 plus f of x2 plus f of x3. So now our job is to figure out what's delta x and what's x0, x1, x2, x3. Okay, so we begin by finding delta x using our formula. Let's do it here. I'll erase it after. But delta x equals b minus a over n. What's b, what's a, and what's n? Well, they give us the interval. They told us that they want this function here on the interval from 0 to 2. That's our starting point, our end point. 0 is a, b is 2. Okay. Which we could see from our graph here. This is our a, this is our b. Okay, so that's done. And they told us there's 4 rectangles. So they told us also n is 4. So we have all the information. Plugging in what we know, we get 2 minus 0 over 4. That means that the length of each interval of our partition is, or the width of each rectangle is a half. Okay, so we're cutting this up into widths of a half. So we're going to stop here at a half. We're going to stop here at a half, 1, 3 halves, 2. Okay, those are our rectangles that we're going to be using. So I'm going to erase this. Keep in mind delta x is a half. That gives us this value here. 1 half, open bracket. Now what we have to do is go find our x0, x1, x2, x3, all that. How do we do that? Well, we use the formula, the second formula that we have. xi equals a plus I delta x. Okay. Well, since it's the left end point, we're starting with x0. You don't have to write all this down, but you could if you want. Well, that means we're starting with a. A we know is 0. So we have 0 plus, and the index that we're starting with is 0. So 0 times delta x. Delta x we know is a half, but it doesn't matter because you're multiplying by 0. So this is all just 0. So x0 is 0. So the first one that we have is f of 0. Okay, just because I don't have room, I'm going to have to erase this. And now what we want to do is 1. The next index is 1. What if we have a 1 here? Well, a remains as 0, and this becomes a 1. The index is 1, because that's where we're at, times delta x. What's delta x? Well, we just said it's a half. We solved it before. So we have 0 plus 1 times a half, which is just a half. So our x1 is a half, as we expect, because our starting point was 0. That was the first value that we got. x0 was 0. The next one, we shift by delta x, we expect it to be at a half. Okay, so this makes sense. So we're looking for f of 1 half. Could you guess what the next term is going to be without using the formula? Well, if we're shifting over by a half, and we're at a half now, that's going to give us 1, right? We expect the next one to give us 1. Let's go ahead and solve it using this formula. x2 equals a, which is 0, plus, since the index is 2, it's 2 times delta x, which is a half. Which 2 times a half? Well, that's a whole. 1. As expected, we're at 1. So f of x2 is 1, and f of x3, without solving using the equation, let's just anticipate what the answer is going to be. Adding a half just gives us 3 halves. So f of 3 halves. Okay. So we found all the x values. Now all we have to do is go ahead and find the y values. Okay, so if I had to draw this, or the rectangles we should envision here, the first one is going to be essentially 0. We expect the area to be 0. The next one, because the left end point is hitting the function at 0, the next left end point is going in the negative direction, so it's going to be down here. The third rectangle, so this is the second rectangle, the third rectangle hits the function at 0 again, so we expect it to be flat, and then the last one hits the function like around here. So we have two zeros and we have one that's negative and one that's positive. That's what I expect my answers to be over here. So let's go ahead and see if that's in fact correct. How do we find this? How do we find f of 0? Well, all we're doing is we're plugging 0 into the function that's given. So f of 0 is 0 squared minus 0, which is in fact 0 as we expected. Plus, what's f of 1/2? Well, let's do that on the side. We're plugging in a half into the function. So f of 1/2 is equal to a half squared minus a half. A half squared is a quarter. 1 squared is 1, 2 squared is 4, minus a half. Finding a common denominator, we get 1/4 minus 2/4, giving us negative a quarter. Okay. So as we expect, our answer here was going to be negative from the graph. We don't need the graph, but it's always good to have a visual and see if the numbers correspond to what we expect. The next one, I'm expecting 0. Let's go ahead and solve it. F of 1, if I plug in 1 into here, 1 squared is 1, minus 1 is 0, as expected. And lastly, 3/4. Sorry, not 3/4, 3/2. Plugging in 3/2 into here, we have f of 3/2 is equal to 3/2 squared minus 3/2. 3/2 squared is 3 times 3 is 9, 2 times 2 is 4, 9/4 over minus 3/2, which is multiply the top and bottom by 2, that's 6 on 4. And 9 minus 6 is 3 over 4, so we get 3/4. Okay. And now we could solve. Negative a quarter plus 3/4, so they have the same base, we just negative 1 plus 3, we subtract the top, giving us 2/4. So 1/2 on the outside, that's on the outside of the square bracket. Inside the square brackets, the zeros we ignore, we get 2 over 4. The 2's cancel, we're left with a quarter. So the area under the curve is a quarter unit squared. That's our left endpoint estimation. Now let's go ahead and look at the right endpoint estimation. So here for the right endpoints, we're going to do it without the sketch, using just our formulas, okay? Just to show you that we don't actually need the sketch. So the first thing we do is we go find our delta x, which we know is b minus a over n. And again, we know the b and the a because we're given the intervals, so it's going to be 2 minus 0 over 4. N is the number of rectangles, they told us it's 4. So again, we get 2 over 4, which is a half. So we have the same width as expected. Now we're using the red endpoint, so R, and we're using 4 rectangles. So we're looking for R4. So the only difference here from the left endpoint is the fact that we're starting at I equals 1. The index is 1. So our formula becomes delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3 plus delta x times f of x4. So here we're starting, instead of 0 and finishing at 3, we're starting at 1 and we're finishing at 4. So technically these first couple of terms here we found already up until 3. We really just have to go find the last one. But let's go ahead and redo it, it doesn't matter. We're going to factor out a delta x, leaving us with f of x1 plus f of x2 plus f of x3 plus f of x4. And delta x we just solved for, it's half. Let's go ahead and find all these terms. F of x1, we have to figure out what x1 is. Again, we use our formula, xi equals a plus I delta x. We know that a is 0, so if we're looking for x1, we're replacing the I, the index, with 1. So this is 1 times delta x. Delta x we said was a half, so we know that x1 was a half, as we saw earlier. So we're looking for f of a half, plus the second one, now we're replacing it with 2. x2 equals 0 plus 2 times a half, which is 1. This is f of 1. x3, we saw this already, so 0 plus 3 times a half. This is 3/4. Three halves. My apologies. It's 3/2. And then lastly, we have x4. I'm running out of room. Let's do it here. x4 equals 0 plus 4 times a half, which is simply 2. And that makes sense because this is the endpoint. We stopped at 2. So this is f of 2. Okay. So now we go find the values of f. by substituting the x values into the original function. So a half squared minus a half, we saw this earlier, so I'm not going to do it again. I'm just going to write the answer. This was negative a quarter. Plus when we plugged in 1, we got 0. We saw that earlier. And when we plugged in 3 halves, we got positive 3 quarters, I believe. Yeah, 9 over 4 minus 3 halves. Yeah, 6 over 4. Okay. 6, 9 minus 6 is 3. Yeah, this is good. Now all we have to do is find f of 2. So f of 2, substituting 2 into here, we get 2 squared, which is 4 minus 2. We get positive 2. So let's go ahead and solve this. So a quarter, negative a quarter plus 3 quarters is 2 quarters plus 2. 2, we could think of it as 2 over 1. And now we can find a common denominator by multiplying the top and the bottom by 4, giving us 8 on 4. So this gives us 2 plus 8 is 10. And on the bottom we have 4. 4 times 2 is 8. Dividing the top and bottom by 2, we get 5 over 4 units squared. So the right hand point is 5 over 4 units squared. And we're done. Let's go ahead and look at the midpoint now. So now for the midpoint, we have to find M4 because we have 4 rectangles. And the formula that we're using is delta x times f of x1 bar plus delta x times f of x2 bar plus delta x times f of x3, all that barred, and plus delta x times f of x subscript 4, all that barred. Okay, so essentially the beginning's the same, so I kept it on the board. We find our delta x, b minus a over n, that's equal to 2 minus 0 over 4, which gave us widths of a half. And then we went ahead and we found our x subscript 0, which was 0, x sub 1 was a half, x sub 2 was 1, x3 was 3 halves, and x4 was 2. So this is stuff we did already in the previous problem, so I'm just rewriting them. Why am I doing this? Because the next part for the midpoint is, well, first of all, the delta x is done, so we could factor that out. We have to go get the bars. Okay, so you have to just remember that the bars is the midpoint of each value. That's all it is. We're just taking the middle of 0 and let's say a half. So you don't have to write the formula, but I always strongly suggest to do that. But intuitively, we should know that I'm expecting my answer to be between 0 and a half. So I'm expecting it to be a quarter. But you could go ahead and solve it. x1 bar is basically just x0 plus x1 over 2. x0 we said was 0 plus x1 is a half divided by 2. 0 plus a half is a half divided by 2, which you could think of as 2 over 1. Flip the second fraction, you get 1 half times 2 over 1 becomes 1 over 2. As expected, we get a quarter. Okay, or a half of 2. Sorry, a half divided by 2 is a quarter. Okay, so x1 bar is a quarter. So factoring out the delta x, we get f of x1. Let's write it x1 bar plus, let's just write it in, x2 bar, f of x3 bar, and f of x4 bar. All this in bracket. Delta x we said was a half, and f of x1 bar, well, x1 bar we just solved for was a quarter. And you could proceed in the same manner by using the formula and solving for it, or you could just take the middle value of the two terms. So we did these two terms, it gave us a quarter. The next two, what's between a half and 1? Well, that's just 3 quarters. So we have f of 3 quarters. And if you're not sure about that, then use the formula and solve for it. And what's between 1 and 3 halves? Well, that's just 1, we could think of it as, maybe it's easier to think of it in terms of 4. If you think of 1 as 4 over 4 and you think of 3 over 2 as 6 over 4, it's easier to catch that in between it's 5/4. Okay. Or you could see the pattern here. 1 quarter, 3 quarters, the numerator is going up by 2. So the next one is going to be 7 quarters. Okay. But these are shortcuts you should do later on. At this point, since you're just learning it, just apply your formula over and over, you'll get these exact values. Okay. And once you have these values, we plug it into the original function, giving us 1 half, a quarter. So a quarter squared is 1 over 16 minus a quarter. 1 on 16 minus a quarter, which is multiply the top and bottom by 4. This is 4 over 16. So we get negative 3 on 16. For the first one, substituting 3 quarters into our formula. Let me just use a calculator for the sake of convenience, not to make silly mistakes. So 3/4 squared minus 3/4. I've got again minus 3 on 16. Let me just double check a quarter. Yeah, that's minus 3 over 16 as well. Plus the next one is 5 over 4. So if we put 5/4 squared minus 5 over 4, I'm getting 5 on 16. And lastly, if we put 7 over 4, square it, and then minus 7 over 4, I'm getting 21 on 16. Okay, so we get a half on the outside. Minus 3, that's minus 6, plus 5 is minus 1. So I get 20 on 16. And 20 divided by 2 is 10, so we have 10 on 16. Both are even, you could divide by 2, so you get 5 on 8 units squared. Okay, so this is the estimate using midpoint rule. Okay, so the actual value, M4 is 5 on 8. The actual value, let's go ahead and look at that. I'm just going to erase this. The area is equal to 2/3, or 0.66 repeating units squared. Okay. Notice that the left endpoint gave us a quarter, which is 0.25 units squared. R4 was 5 over 4, which is 1.25 units squared. And then the midpoint is 5 on 8. So 5 on 8, let's take a calculator, is about 0.625 units squared. So we could see that the midpoint was the best approximation to the actual value. The actual value was 0.66. We could see, we're going to learn how to solve that later on, but for now, you can just trust me, that's the actual value. And here 0.25 is the lower bound. The right endpoint gave us 1.25, which was an upper bound. These are really off. Notice the midpoint, 0.625, very close to the actual value. So upon deliberation, let's not just believe me because I'm saying the area is 0.66. Let's go ahead and show it. So how are we going to do this? Well, we're going to take the rectangles to be n, and we're going to take the limit as n goes to infinity. We're going to use, you can use left endpoint or right endpoint, it doesn't matter. I'll use right endpoint. Okay, so the solution. We want the actual value of the area. So we're going to use the limit as n goes to infinity of delta x times f of x1 plus delta x times f of x2 plus dot 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 plus delta x times f of x n. Okay. We're using n rectangles, so the width of each rectangle, let's go ahead and find that. Since we're still working on the interval from 0 to 2, well, we could get our delta x. How? Delta x is equal to b minus a over n, which means that delta x is equal to 2 minus 0 over n. That means each delta x is equal to 2 over n. That gives us the value of delta x. Let's go ahead and pull that guy out. So I'm going to factor out the delta x from each of the terms, and at the same time just rewrite it with 2 over n. So we know that delta x is equal to 2 over n. What we're left with is the sum of f of x1 plus f of x2 all the way to f of xn. Let me just erase this. This is done. F of xn. Okay. So we know delta x is equal to 2 over n. Let's go ahead and find the values of x. What's the value of x? Well, each x is a plus I delta x. A, we said the starting point is 0. I is just the index. We have to keep it for now. And delta x, we said, was 2 over n. Oops, not 2 times n, 2 divided by n. This means that xi is equal to 2i over n. Okay. So that's each one over here. This is equal to the limit as n goes to infinity of 2 over n of times f of x1 we could rewrite this as the sum I equals 1 to n of f of xi. Okay. Because we're adding them all up, and the only thing that's changing is the subscript, so we call that index I. We're starting at 1 and we're finishing at n. So we could rewrite it in this notation. The reason why I'm writing it in this notation is to replace the xi with what it's equal to. Xi is equal to 2i over n. So let's go ahead and do that. That gives us the limit as n goes to infinity, 2 over n, the summation I equals 1 to n of f of 2i over n. Well, what's f of 2i over n? Well, we know that f of x is equal to x squared minus x. So that means f of 2i over n is equal to, well, whatever's in the bracket, we're going to put it over here, square it, and then subtract by it. So whatever's in the bracket, we're going to square it. So 2i over n squared, and then subtract by the same thing. Subtract by whatever's in the bracket. So minus 2i over n. So that's what we have over here. So let's go ahead and write that. That gives us limit as n goes to infinity of 2 over n times the summation from 1 to n of this thing over here. So 2i squared. Let me simplify this. So 2i squared over n is really just 4i squared over n squared, right? The 2 gets distributed to each term. So 2 to the power of 2 is 4, I to the power of 2, I squared, n to the power of 2, n squared. So this piece is done, minus 2i over n. So this piece is done here. And now we could deal with each term individually. If you're thinking of factoring out a 2i over n, that would work as well. You could do that. I'm going to deal with each term individually. So I'm going to distribute the 2n to each term, and that's going to leave me with the limit as n goes to infinity. The first one over here, and I'm going to take the sum of each term individually as well, right? Because it's separated by a minus. We could do that. That's one of our properties. So over here, what I get is on the outside, I'm going to factor out the 4 with the 2 giving us 8. And I'm going to take out the n squared with the n, giving us n cubed, times the summation I equals 1 to n of, if I took out the 4 and the n squared, I'm just left with I squared. This is something that we know, right? That was distributing the 2 over n to the first term. Now I have to distribute the 2 over n to the second term, and recall that this guy also has a sum. So if I take out the 2 over n, I'm left with 4 over n squared. And the sum from I equals 1 to n, so I'm taking the sum of each term individually, I'm allowed to do that, and at the same time I'm factoring out the 2 over n with this one here, giving me 4 over n squared. Because remember, we have to distribute this to both terms. Don't multiply only the first term, that's a common mistake. And we're left with just I here. And this is a formula that we know as well. We know both these formulas. So let's go ahead and plug them in. Limit as n goes to infinity, we have the 8 over n cubed. And the formula for the sum from I to n of I squared, we know it to be n times 2n, oh sorry, that's the wrong formula, n times n plus 1 times 2n plus 1. All that over 6. Oh, sorry, not plus, minus. We have our 4 over n squared over here, and we know the sum of I. I is just n times n plus 1 over 2. Okay. So let me take a shortcut here because I'm running out of room. Here, all we care about again is the highest exponent. So the highest exponent that we have here is multiplying n times 2n, right? So this is going to result in 2n cubed, right? So we have 2n cubed, and on the bottom we have n cubed. And since the exponent of the numerator and denominator match, we know the answer is just going to be the coefficient, leaving us with 2 times 8 divided by 6. So that gives us 16 on 6, which is divided by 2, 8 on 3. Okay, this gives us 8 on 3. If you don't believe me, distribute it, take the limit, and you'll see you'll get the exact same answer. You can work out the details. Okay. On another way, you could cancel out the n with one of these guys. You're left with n squared, and it makes life easier. You could just distribute the numerator, and you have n squared on top. But anyways, we get 8 over 3 minus, here same reasoning. The highest exponent on the numerator is n squared, because n times n is n squared, and the highest on the denominator is n squared as well. So we take the coefficient in front, leaving us with 4 over 2. 4 over 2 is just 2. So 8 over 3 minus 2. 2 is just you can think of it as 2 over 1, which is 6 over 3, and 8 over 3 minus 6 over 3 is 2 over 3, which is 0.66. And this is the actual value. So in the next example over here, it says to estimate the area under the curve, the following function using the left and right endpoints on the interval from 0 to 4, and they tell us to use 4 subintervals. So we're going to partition this into 4 subintervals. Let's begin with the left endpoint. And notice that they don't actually give us a function, they give us a sketch of a function. It's actually easier this way. What we could do is use our formula. So left endpoint, it's still L4 because we have 4 subintervals. This is our A, this is our B. And we're looking for, since there's not n subintervals, we're not using the limit, we're just going to use delta x times f of x. Left endpoint, we're starting at 0, plus delta x times f of x1, plus delta x times f of x2, plus delta x times f of x3. So we stop one short from this number here, as we expect, because we started at 0. So delta x, we could go ahead and find that. One of the first things you could do is find delta x. So delta x equals b minus a over n. B is 4, a is 0, n is 4. So 4 minus 0 is 4, divided by 4 is 1. So the delta x, the change in x, is 1, as we would expect, because we're taking the interval from 0 to 4, and we're partitioning into 4. So we're cutting it up into 4 sections, meaning that the width of each section is going to be a distance of 1. So this is something that we would expect, but let's just write it down here so that we have it, we're showing our work. So delta x is 1. If I factor out a delta x, I'm factoring out a 1, so it doesn't change anything. So we're really just looking for f of x0 plus f of x1 plus f of x2 plus f of x3. Okay, so we have to figure out what's x0, x1, x2, x3. Intuitively, you can figure this out. What's our x1, what's our x2, x3? We could see it from the graph, but let's go ahead and solve it using our formula. Because the numbers won't always work out to be nice like this, they might become difficult, as we saw in the previous example. So xi equals a plus I delta x. A is the starting point, which we know is 0. I is the index. And delta x is, we found is 1. So if we're looking for x1, it's going to be 1 times delta x, which is 1, giving us 1 times 1, which is 1, plus 0 is 1. Okay, so x1 is 1. Let's write that here. This is x1, this is x0. Shifting over by 1, this is our x2, x3, x4. Okay, so we don't really have to go ahead and solve it. If you want, you could continue the list and go find all the x values, but we know it's shifting over by 1, so we could pretty much take this as a given. And we move on to the next part. So we said delta x is 1, so I'm not going to write it. This is 1. And we said f of x0, x0 was just 0. Plus f of x1, which is 1, plus f of x2, which is just 2, plus f of x3 equals 3. Okay, so usually at this point here, we substitute these values into our function, but we don't have the function. How do we do this? Well, we just read it off the graph. What's f of 0? This is asking us, when your x value is 0, what's the y value? Well, at 0, when do we hit the green function? Well, we hit it by reading the graph at 2. So f of 0, the y value when x is 0 is 2. So this is just 2 plus, what's f of 1? Well, when x is 1, what's your y value? When do we hit the function? We hit it at 3. So plus 3. When do we hit 2? When x is 2, what's our y value? 2 is 1. Plus f of 3, when x is 3, our y value is 0. So this is 2 plus 3 plus 1, which gives us an answer of 6 units squared. So the approximation, the left approximation, is an answer of 6 units squared. Let's go ahead and see the right approximation. So using the right endpoints, we are looking for R4 because the number of rectangles that we're using is 4. Delta x ends up being the same thing, so I'm going to keep it. But the formula that we're using now is delta x. I'm going to factor it out right away. And we're going to write, since we're doing the right endpoint, we're starting at 1. So the index here is 1 plus f of x2 plus f of x3 plus f of x4. So we ended at 4. Delta x we know is 1. We solved for that already up here using the formula b minus a over n. gave us 1. So what we're left with is f of x1. x1 we saw before using the formula, x1 was 1, x2 was 2, x3 was 3, and x4 as expected is 4. You can use the formula if you don't believe me. Go ahead and solve that. And now to find 1 to f of 1, f of 2, f3, and f4, we again read the graph. So f of 1, when x is 1, what's my y value? It's 3. When x is 2, what's my y value? It's 1. When x is 3, what's my y value? It's 0. And when x is 4, what's my y value? At 4, we read up here, hits at 2, giving us an answer of 3 plus 1 plus 2, which is 6 units squared as well. Okay, so the left hand point and the right hand point ended up being equal. Does that mean that the area under the curve is necessarily 6? Not quite. We have to be more precise. The widths that we're taking are a distance of 1. That's large. We want to be as precise as possible, so we would take these to be a lot smaller. So if you use a distance of a quarter, let's say, and partition this into, what's that, a quarter times 4, 16 rectangles of length a quarter, you would get a more precise answer. So before you assume the answer is actually 6, because at this point the estimates were, the left and right hand point were 6, doesn't necessarily mean that we're going to fall in between that, okay? So be very careful with that. The smaller you are, this is what you have to keep in mind, the smaller the rectangles are, the widths of the rectangles are, the more precise your answer is going to be. Okay, so let's take a look at our final example. So in this example over here, it says to express as a limit the area under the curve of f of x equals 1 over x from 1 to 3 using n subintervals. So here we don't have a polynomial function, we're actually dealing with a rational function. Why is this an issue? The issue is that we won't be able to actually solve it or evaluate it because we know our summation formulas for constants. We know it for I squared, and I cubed. This means we could only deal with polynomials of degree 3. Okay, we don't know how to deal with rational functions. So let's go ahead and just set it up, and we'll see how to actually solve these problems later on. Okay, but let's set up the limit. So to find the area, first of all, a is 1, b is 3. Let's start off by finding our delta x. And I'm going to use, when it doesn't state it, I'm going to assume it's right endpoints. Okay, so delta x equals b minus a over n. This is our formula. B is 3, a is 1, n is n because they don't tell us. We're using n subintervals. So this gives us 2 over n. That's our delta x. Next, let's go find our xi. Xi equals a plus I times delta x. A we know is 1 plus I times delta x. I is the index, and delta x is 2 over n. This means that xi is equal to 1 plus 2i over n. Okay. So now to express the area as a limit, the area equals the limit as n goes to infinity of delta x times, I'm just going to factor out the delta x right away just because it's simpler. All the terms have a delta x, but I'm just going to factor it out. And the first term, since we're using the right end point, I'm starting with x1 plus f of x2. Sorry, went a bit crooked here, but all the way to the last term, xn. Okay. So our job now is to figure out the x's, but we can rewrite this as a sum. So we can rewrite this as the limit as n goes to infinity of delta x times this summation. So in the square brackets, we have the sum starting at 1 to n of f of xi. So the only thing that changes are the subscripts, and it starts at 1, finishes at n, so we have the summation because we're adding them from 1 to n of f of xi. Okay, so we do this because we could substitute xi with what it's equal to. We know xi is equal to 1 plus 2i over n. Let's go ahead and do that. Limit as n goes to infinity, and we know what delta x is. We solved for it. Delta x is just 2 over n. So I'm going to replace it with 2 over n, and then I'm going to replace the summation with whatever xi is. Xi is 1 over, f of 1 plus 2i over n. Okay, and the function we have it's 1 over x. So this is equal to the limit as n goes to infinity of 2 over n times the summation I equals 1 to n, and it's going to be f of x. So x, you take whatever x is and you do 1 divided by that answer. What's x? What's in the bracket? We're going to do 1 divided by this answer. So we have 1 over 1 plus 2i over n. Okay. And unfortunately, we have to leave our answer in this manner. There's nothing more we could do. So this is the limit that represents the area. Okay. Because the I is on the denominator, so we don't have a rule for the summation of, let's say, 1 over I. Okay. We just know constants I squared, and I cubed. Okay, so this is our final answer. Okay, so I hope this helped. I hope you have a better understanding of Riemann sums, and I'll see you in the next video. Keep practicing.